how do we interpret the values of the Michaelis-Menten constant and Vmax? Take note that these values are accurate only if the enzyme follows the first postulate of Maude-Menten and Leonor-Michaelis. So their postulate is that you have two steps in the catalytic action. So you have the formation of the complex, followed by the release of the product from the enzyme substrate complex. Recall that your Michaelis-Menten constant is equal to K sub negative 1 plus K2 over K1. So again, if we consider that the second step in our reaction is the slow step, it means that K2, or the rate constant for the second step, is smaller than the rate constant for the forward and the backward rate constants for the forward reaction and the backward reaction of the first step. So K2 is smaller than K negative 1. And if we say that the value of K2 is negligible, then our Michaelis-Menten constant becomes K negative 1 over K1. And this is what biochemists call the dissociation constant. So the dissociation constant refers to an equilibrium process, which is the dissociation of the enzyme substrate complex. So again, we assign, so this time for the forward, we have the K negative 1 so that we are consistent with these rate constants. And for the backward, we have K1. So recall the definition of equilibrium. So when we say equilibrium, the rate of the forward reaction is equal to the rate of the backward reaction. So the rate of the forward reaction is K negative 1 times ES, and the rate of the backward reaction is K1 times E times S. Again, we can we can write the equilibrium constant expression for a reaction reaching a state of equilibrium as the ratio of the concentrations of its products to the concentrations of its reactants. So in this case, we only have one reactant, which is the complex. So if we try to derive this or obtain this expression from this equation, then we will have K negative 1 over K1 equal to E times S over ES, which is the equilibrium constant expression, more commonly known as the dissociation constant. This is the reason why a lot of biochemists associate the Michaelis-Menten constant with the affinity of the substrate to the enzyme. But again, this is only if the enzyme follows this two-step mechanism. So if it does, then the value of the Michaelis-Menten constant is also equal to the dissociation constant. And if this has a very high value, it means that your substrate tends to dissociate from the complex. And if this has a low value, then we can say that the substrate has high affinity for the enzyme because it doesn't easily dissociate from the complex. So again, the Michaelis-Menten constant is not a measure of affinity. So it's not a definite measure of affinity between the substrate and the enzyme. So the more general definition for the Michaelis-Menten constant is if we take this condition wherein the initial velocity is half of the Vmax and substitute this to our original equation, so we have Vmax over 2 equals Vmax times S over S plus Km. So we can cancel out Vmax. And if we um, cross multiply this, so we have S plus Km equals 2S. So Km is equal to the concentration of the substrate. So if we have the initial velocity exactly half of the maximum initial velocity, then the concentration of the substrate at that point is the Michaelis-Menten constant. So this is the definition of Km. So Km has units of concentration, so it can be molar, millimolar, or micromolar. Now, how about Vmax? So Vmax again tells us the maximum initial velocity that an enzyme achieves on its substrate if the mechanism is the two-step one postulated by Menten and Michaelis. Now, if the enzyme doesn't follow the two-step mechanism, then it is a bit complicated because your Vmax is not accurate. The it is not exactly the maximum velocity or initial velocity that your enzyme can achieve. So if we have the two-step mechanism, then recall that your Vmax is defined as the rate constant of the second step times the total concentration of the enzyme. Now, if the enzyme follows a different mechanism, for example, you have the first step, which is the formation of the enzyme substrate complex. Your second step is the formation of the enzyme product complex. And then the third step is the release of the product from the enzyme. And this is your uh, rate determining step. Then your Vmax should be a value that is dependent on the value of this rate constant, the rate constant for the slow step. So all of these, you don't have to be very particular about these information on your Km and your Vmax. So as long as you know that these parameters are based on the two-step mechanism, then you know how to interpret them properly.